on that. Now, something similar happens in a compound microscope. Compound microscope, the basic difference between simple and compound microscopes is that it uses two lenses instead of one. And why use two? Compounding effect. The first lens will magnify the image a little bit. The second lens will magnify it further. So the magnified image is further magnified. Did you understand?
Yes, sir.
Okay, fine. Now assume this is the first lens having focal length f1. It's a convex or converging lens only because diverging lens forms a diminished image. We don't want that. We always use converging lens only in a microscope. Assume the focus is here. Same distance I'll mark on the other side also. These points help us in ray diagrams. If this is f, then somewhere here will be 2f. Okay. This is a converging lens. A converging lens produces magnified images in two cases. First case is when the object is within the focal length. When object is within the focal length, as we have just seen, okay, you can draw one ray like this, another ray like this, roughly I'm drawing. You will get image somewhere here. Fine. If object is within the focal length, you get the image here and it will be a virtual image. Fine. It's a magnified image, good. And that image can act as object for the next lens. Everything works well. But there is a problem. What do we want here? We want the magnified image formed by the first lens to be further magnified by the second lens. Okay. That is where the problem arises. Not problem actually. That is where there is a restriction, you can say. For the second lens to be able to magnify, this first image that is formed should fall within its focal length. See, for the second lens, I'll draw the focus in yellow or green, let's take. Let's say this is the focus of the second lens. And if that distance is f, then 2f may be somewhere here. On either side, I'm taking 2f. A converging lens can magnify only if the object lies within this range of distances. Okay, up to 2f. Now look at what is happening here. The first lens is forming an image behind the lens. How will that image I fall within this distance of the second lens? That's not possible. Rishi, yes or no?
Yes, sir. So,
That image I cannot fall in this range of distances. So this is not the case we are looking for. So for a compound microscope to work properly, the object must not be placed within the focal length of the first lens. You should not do that. Okay, so what should we do? You should place the object between f and 2f from the first lens. Why? If you place the object between f and 2f, okay, let's say this is the original object of height h. Basic ray tracing we will do. We draw one ray parallel to the principal axis. After refraction, it will pass through the focus on the other side. So that's how it goes. And we draw another ray directly through the optical center. And what will happen to that one after refraction? It passes without any deviation. Continues like this. So the two rays meet here. That is where the first lens forms an image. And you can clearly see the image is bigger than the object itself. Rishi, do you agree with this or not?
yes, sir.
Okay. Now, because the image is bigger than the object, it's a magnified image, that's fine. And because the image is forming on this side, we can make it fall within the range that we expect to. Yes or no?
Yes, sir.
Now the second lens also will be able to magnify it. If the image forms on this side, if the first lens image forms on this side, as shown in this diagram, the second lens will be able to magnify it. Okay. So fine, let it be like this. We'll consider the second lens a little later, but let's see what the first lens has done. First lens has produced a magnified image. Let's say image height is h1. Object height is small h, as you can see. And this distance is the object distance, and this distance is the image distance, clearly. Okay. Then we can say that h1 by h is equal to v divided by u. Basic magnification produced by a lens. Linear magnification. Height of image by height of object is v divided by u. Is this clear?
Yes.
Okay. Now what happens is this image that is formed by the first lens will be further magnified by the second lens. Let's see how it does that. The ray diagram is the most important thing. That's why I'm explaining briefly. I mean, slowly, not briefly. So we know that the image formed by the first lens behaves as an object for the second lens. Okay, let's call this image as I1. I1 is the object for the second lens now. Okay. And we want another magnified image. We want further magnification. Fine. Let me adjust the ray diagram. We'll cut it till here. That's where the first image is forming. That now behaves as an object for the second lens. What we will do is we will place the second lens very close to this object. How close? Such that this object falls within the focal length of the second lens. Focal length of the second lens, call it f2. Assume its focus is here. The image formed by the first lens should fall within the focus of the second lens. Okay. Now we do the ray tracing again. From H1, if you do the ray tracing now, one ray travels parallel to the principal axis. Now you may ask, sir, how is this ray even being produced? The original rays were going like this. Where did this ray come from? Okay. Now these two, first and second, these two are not the only rays participating in image formation. There will be infinite other rays participating in image formation. For example, there will definitely be one ray passing like this also. To locate image position, we just draw two rays, but rays will be passing from the other points of the lens as well. Okay. There will be infinite rays involved in the formation of an image. So one of those rays will go that way. Nothing wrong in that. So I1, which is the image formed by the first lens, is an object for the second lens, and we are doing ray tracing for that object. One ray travels parallel to the principal axis, and after refraction, it passes through the focus this way. And another ray is drawn straight through the optical center, and after refraction, it passes this way. And as you can see, these two don't meet after refraction. So basically what happens is they appear to be coming from somewhere behind. Maybe, okay. The image seems to, or the rays seem to be coming from somewhere here. So this is what is the final image. Okay, I'll draw it in bold. Let's call this final image as I2. That is where the rays finally appear to be coming out from. Okay. And if the observer's eye is on the right side, that is what the observer will see. Okay, Rishi, just think about this once again. Ask if you have any doubts. Is it clear what the compound microscope is doing?
Yes, sir. It takes the image of the first reflection, and
Refraction.
then yeah, and then it takes that and then
Magnifies it further. Okay. Right. So if there's an observer over here, the rays will enter into the observer's eye as if they are coming from I2, and I2 is what the observer will finally see. Okay. Right. Now, what we look for in a microscope is magnification, angular magnification. And what is angular magnification? The final angle subtended by the image on the eye when seen through the instrument divided by angle subtended by the object on the eye when seen directly. When we look at the object directly, okay, we discussed that yesterday itself, yesterday or last class. When we look at the object directly, the angle it forms on our eye or subtends on our eye is h by d, where h is the height of the object, original height of the object, and d is the near point distance. Okay, that's the angle it subtends when we see it directly. When we see it through the instrument, okay, which is a compound microscope now. When you see through a compound microscope, see the angle that it finally subtends on your eye. This is what we are looking for. Okay. Let's derive an expression for theta now. You see there is a small triangle here. H1 is the height of the image formed by the first lens that we have already discussed. That image formed by the first lens behaves as an object for the second lens. Assume it is placed at a distance small d from the second lens. Then we can say that, Rishi, tell me, what is tan theta equal to from this diagram? Opposite by adjacent, how much is it?
H1 by D, sir.
Correct. H1 divided by small d. And see, for our visualization, we show exaggerated angles like this, but all the optics that we are discussing now is valid only for small angles. So theta will also be a small angle in real life. No object that you see through a microscope will be subtending such a large angle on your eye. Fine. So theta will be a small angle, and for small angle, tan theta is nearly equal to theta. You can write theta itself is h1 divided by small d. Small d is the object distance finally. Okay. But h1 is the height of image formed by the first lens. We have no idea of h1. We don't know how much it is. Small h we know. That's the height of the object. Okay. So we'd like to convert theta to small h terms instead of capital H. And we already discussed, sorry, why did I say capital H? We would like to express theta in terms of small h instead of h1. Okay. So we use this ratio h1 by h is equal to v by u. In fact, if you just take their magnitudes, it should be minus v by u, because in this diagram, image distance is positive, object distance is negative. Positive by negative will come out negative. You multiply it with another minus sign, the ratio of heights will be positive. So you can say that h1 is minus v by u into original height of the object. We will use that here. Therefore, the angle theta subtended on the eye becomes h1 into 1 by d, and h1 is original height into minus v by u multiplied with 1 by d. That is the final angle subtended by the image on the observer's eye when the observer looks through the compound microscope. And see, compound microscope has two lenses, as you can see. The lens which is close to the object, it's called the objective lens. And the lens which is close to the eye is called the eyepiece. So instead of calling the focal lengths f1 and f2, you can call them as fo and fe, or f0 and fe. Anyway, this is the final angle subtended on the eye. Therefore, the angular magnification produced by a compound microscope, final angle divided by the original angle subtended. Final angle is all this, small h into minus v by u into 1 by d, divided by what was the original angle subtended when seen directly? Small h divided by capital D. Small h cancels. What will you be left with? Minus v by u into capital D by small d. Rishi, is this clear?
Yes, sir.
What is u in all this?
It's image distance.
U is always object distance. Okay, u is the distance where the object is placed from the objective lens, first lens. Okay. V is where it forms the image. So if you want to find out the overall magnification produced by a compound microscope, overall angular magnification, you need to know where the first lens is forming the image. Or you need to know the magnification produced by the first lens. Then only you can tell the overall magnification. So basically this part here is magnification produced by the objective, and this part here is magnification produced by the eyepiece, capital D by small d. In fact, for simple microscope also, the magnification was capital D by small d itself. Because in simple microscope, you only have one lens. That one lens produces magnification capital D by small d. In compound microscope, you have two lenses. One lens produces minus v by u. The other lens produces capital D by small d. Multiply them, you get the overall magnification. That's why it's called compounding. Magnification gets multiplied. Is this clear? Now in your textbook,
Yes, sir.
this magnification produced by a compound microscope is expressed in a slightly tricky way. Okay. What they assume is they take only one case, final image forming at infinity. But what we have shown here is the general expression for magnification produced by compound microscope. Now, V is where the first lens forms the image. U is where the original object is placed. Capital D is near point distance. What is small d? Small d is the distance from the image formed by the first lens to the second lens. And by adjusting small d, you can adjust where the image forms. Okay. So in your textbook, they take one case. They make the image form at infinity. For image to form at infinity, small d should be the focal length of the eyepiece. So they take it off like that. Okay. They take small d as the focal length of the eyepiece, assuming final image forms at infinity. So they have given only one case, but we are discussing more generally. Therefore, magnification produced by a compound microscope is minus v by u times capital D by small d. I'll write it as capital D into 1 by small d. Rishi, tell me, from what we derived in the last class and even today in the beginning, what is 1 by small d equal to in terms of x and f?
F plus x by fx.
Okay, 1 by f plus 1 by x. We'll keep it like that. What you said is also correct. That is after taking LCM. We'll keep it as 1 by f plus 1 by x. Now, whose focal length is this? Focal length of the eyepiece, second lens. Okay. Now, x is the final image distance. So, using this formula, minus v by u into d into 1 by f plus 1 by x. Using this formula, you can tell the magnification produced by a compound microscope for any image distance, not just at infinity. Okay, so this is the general formula for magnification produced by compound microscope. Okay, we'll solve one problem based on all this. So remember, in a compound microscope, there are two lenses. The first lens produces a magnified image, I1. That's a real image. And why do we want that image to form on the right side? Why not a virtual image on the left side itself? Because if a virtual image forms on the left side, this lens won't be able to magnify this because it is too far from that lens. Okay. A lens can magnify an image only if, sorry, a lens can magnify an object only if it is within 2f, within a distance of 2f. Beyond 2f, you will get diminished image only. Okay. That's why we want the first lens to form an image on this side. And that image I1 formed by the first lens behaves as an object for the second lens, which magnifies it further. And the final image that you see is I2 that is shown in this diagram. Okay, this is what we finally see. Okay. I'll give you this diagram also. Just derive magnification in one case. And what we are looking for is angular magnification only. Whether it's simple microscope, compound microscope, or telescope, we are interested in angular magnification. So what all do you need to know for magnification? You need to know where the object is placed first of all, and you need to know the focal length of these lenses. So let's say the objective lens has a focal length of 10 centimeters. I'm just taking some random values. Let's say it is 10 centimeters, and eyepiece focal length, assume it is 20 centimeters. Okay. Now for the compound microscope to work as intended, object must lie within this range between f and 2f. So it should be between 10 and 20 centimeters. I'll keep the object at 15 centimeters from the lens. Okay. You can find out where it forms the image. So you can find out V, and near point distance is given to you 25 centimeters because the magnification formula has near point distance in it. That is given 25 centimeters. Focal length of the eyepiece is given to you, and I need to tell you where the final image should form. Based on that, you can tell the magnification. So first case, or let's take one case itself. If the final image forms at infinity, how much is the angular magnification produced by this compound microscope? Try to solve this. Right. Rishi, how have you tried to solve this? We need magnification produced by the compound microscope. So tell me.
So the formula is minus V by U into D into 1 by F plus 1 by X.
Correct. 1 by Fe, focal length of eyepiece, plus 1 by X. That X is where you want the final image to form. Yes. What all do
Sir,
you
the
all?
confusing part is the
Go
sign
ahead.
convention.
For the first lens.
They're like let's say we take the incident, we take the first lens as plus and the right side of the first lens is minus.
See, Rishi, it's not your choice. Which side you take plus depends on how the rays are traveling. Tell me in this diagram that you see on your screen, from which side to which side are the rays traveling through the first lens?
From the left to the right, sir.
Correct. Okay. The direction or the side to which the rays are traveling must be taken positive. It's not your choice. So anything to the right of that lens is positive. Anything to the left of that lens, any distance to the left of that lens is negative. Okay.
Yes, sir.
So you look at the formula for magnification produced by compound microscope. In this formula, what all do you already know from the problem?
We know V, which is infinity.
In the formula, what does V mean? Okay, that's why the ray diagram is very important. V is not the final image distance. V is the image distance from the first lens. Okay. V is this distance. So you need to find out where the first lens forms the image. That is unknown. Do you know where the object is? Original object?
So that's U.
How much is that distance? Wait, where is the problem that I gave? Yeah, in the problem, how much is U?
15, sir.
Should you take it as plus 15 or minus 15?
Minus.
Okay, so U is known to us. Fine. V is unknown. U is known to us. It is minus 15 centimeters. Okay, all distances will be in centimeters only. How much is capital D, the near point distance?
$25.
25 centimeters. How much is the focal length of the eyepiece?
10 centimeters.
Look at the diagram clearly and tell.
Oh, yeah, 20.
The lens which is closer to the object is called the objective. The other lens is called the eyepiece, 20 centimeters. Where do we want the final image to form?
At infinity.
Okay. So to derive magnification, what is the only thing you need to find out?
V.
Yes. We need to find out where the first lens forms the image. Apply the lens formula and do that. Apply lens formula to the first lens and find out where it forms the image. This distance. Formula. So 1 by V minus 1 by U is equal to 1 by F. Focal length of the objective is 10 only. So you get 1 by V is equal to 1 by 10 minus 1 by 15. 10, 15 LCM is 30. 3 minus 2, 1 by 30, you get V as 30. Correct. Substitute it there, that's all. There you have the magnification now. V is 30. So the whole thing, minus 30 by minus 15. Effectively, what does it become? 2. Near point distance is 25. And 1 by infinity is 0. 1 by FE is 1 by 20. 2 into 25 is 50 by 20 is 5 by 2, that is 2.5. That's the magnification you get. Okay, if the final image forms at infinity, the magnification you get is 2.5 using this compound microscope. Now, depending on where you want the final image to form, the magnification will change. So remember, simple microscope, compound microscope, and even a telescope that we are going to discuss next won't have a fixed amount of magnification. You can adjust it depending on where you make the image form. In fact, you can adjust it depending on where you place the object also. Okay, because U dictates V. Fine, magnification depends on V, no? So where you keep the object decides where the first image is formed, V. And then where you want the final image is also up to you. That should be given in the problem actually. Okay. The next thing to discuss is telescope. We'll discuss it in tomorrow's class. I'll take a short session tomorrow. We'll discuss what do you call magnification of a telescope, astronomical telescope, and or the terrestrial telescope also. But what I suggest is you draw ray diagrams. I've been telling you this in all classes. Draw ray diagrams for simple microscope image formation, which is this one, and compound microscope image formation. From ray diagrams, you try to derive the expression for magnification, then you will understand better. Okay, fine. Thank you all. We'll close it here. We'll continue tomorrow. Okay.